Our today's guest is Mudit Gaur, who is going to talk about learning to learn under uncertainty on efficient and scalable bi-level reinforcement learning.
Right. Thank you for coming, everyone. Good afternoon. So thank you, Professor, for introducing. So today, the title is, as Professor just mentioned, Learning to Learn Under Uncertainty. So the title sort of talks about learning to learn, which is saying that it's a more complicated form of reinforcement learning, where there are other additional uncertainties about the environment. So since reinforcement learning is, learning about how to act in the environment, this additional complication sort of tells you how you learn to learn. So how you learn to get good policies or rules to learn environment under these additional uncertainties. And then in this talk, I will talk about how we can make more efficient and scalable methods to do this particular thing.
So is it also meta-learning? Is this meta-learning also?
Meta-learning is going to be one of the things where this framework applies.
Mm-hmm.
So, just a second. Okay. So before we talk about things like bi-level RL, which meta-learning is a part, it would be good to first give an overview of, what RL or reinforcement learning is. And from the point of view of examples, I think it's one of the most ubiquitous and widespread things in all of, not just computer science, but like in all forms of engineering, even medicine. So all the way from things like the ads you get targeted to, training your large language models, drug design, self-driving cars. All of these have sort of exploded in terms of popularity and their widespread usage. This chart that I have here is from a paper just titled Deep Reinforcement Learning. So the sort of the spark that ignited all of this was the usage of deep neural networks in reinforcement learning that made them so widespread and ubiquitous. Now, before we talk about bi-level RL, it's important to give a sort of a, introduction into the structure of RL. As the name suggests, reinforcement learning means that as you interact with the environment, you get a reward, something that either it's obvious from the setup of the structure or something that you define yourself. So for example, let's say there's a task of locomotion. So a robot is trying to go from one point to another. You can say that the reward is that if it's not hitting anything, you can give it a reward of 0 or +1. And if it hits anything, you can give it a reward of, negative, large negative number. The bigger you make that negative number, the less likely the robot is to hit, or the more incentive that it has to not hit. And once you have defined this kind of structure, the robot can, try out different paths and sort of by itself come up with sort of a policy or a rule about how to navigate an environment. Now, a key part of what I just described is this fact that it's either obvious from the environment or we decide for ourselves what the reward is. In some real life situations, it might be obvious what it's going to be, or in terms of, if it's something that the robot did is good or bad. So you can give it a 0, 1, or you can give it a quantity that you can decide for yourselves. But for the most part, the reward is quote unquote known, not deterministic. There can be, but you can know, okay, this is my reward. Now, while this was true for a lot of things that I talked about, recently there have been situations where this paradigm is not something that is feasible. It just does not fit into what is being needed to be done. A very big example of this is recently what is known as reinforcement learning from human feedback. It is one of the most important things that have allowed large language models to become as good as they have. So I'll just give a very brief overview of how the training of a large language model works. There are people here who have known this in much more depth, but I'll just give a quick overview. So the first step, known as supervised fine-tuning, sort of has a couple of phases where once you have what's known as the true pre-training phase, where you take a large amount of data and then you train your model on it. That does not involve any reinforcement learning. It is done by traditional supervised learning methods. And then you have fine tuning of that where you give it more curated data sets. This is especially true from custom large language models. If you want to have, for like coding or, some sort of drug design and so on and so forth. So that part was initially how the large language models were being trained. What has allowed them to become so good is this incorporating human feedback into them. And what that means is that you take a large language model and you have two different, or it can be n different. Two is the more commonly used. You can have two responses, and then you can have human annotators. And then you can have human annotators say which one of the responses is good, is one or the other, or you can even have them rank the responses in order. And then what you can do is you can, instead of what we talked about earlier, where the reward is, oh, if you don't hit something, the reward is 0 or 1. If you hit something, it's negative, a large quantity. The reward is now a function itself. It can be a parameterized function like a neural network. And you can say, I'm going to change my neural network to align with these preferences. And then once you have enough of that data, you can say, okay, now that I have aligned my reward with these preferences, now this is my reward function. So that's the improved reward function based on human feedback. And then you run your reinforcement learning on that learned reward function. So this is what's known as optimization. And one of the key things is that there is a unique type of optimization called proximal policy optimization that people at OpenAI, notably John Schulman, came up with, which is the reason why their models are so good. But the key thing here is that we no longer have a reward that is known. The reward itself is something that is to be estimated from data. And of course, it's not perfect. Human annotators, just like with everything else, can have their own biases. So it's an ongoing process. There's much research going on in how that can be improved. But the point is that the reward itself is a function that is to be estimated. Now, the picture that I had before is kind of sort of implying that it's like a one-off process. It's one in sequence. Usually it's done in more iterative manner. So you have your annotators, they get, they annotate data, this one is better. And then the policy is trained. And that policy itself then generates a couple of responses and the human can tell which one is better. And then so there's like a continuous process. It's an iterative process. So this is what is known.
What goes?
Sorry?
So you have the two arrows.
Yeah.
What travels along the back arrow?
So it's like, so let's say you are training your reward, right? So now you have kind of a reward, which is a neural network. So the lower arrow will implies that this algorithm that's running, the PPO, now has that particular reward parameterized with those updated parameters that is used for training the policy, running the PPO on that. And then once you have that model can then be used to generate those two rewards that can be annotated by the human feedback. It can be a human, or it can.
So what travels along the back?
This one, the lower one.
No, the back arrow.
Oh, this one. So this one means that the data that is now being used to improve the reward is being generated from this policy that you have used. There's kind of a link between those two. That's going to be like a key issue that we focus on. So these two are linked. And apart from that, so I know that RLHF is typically associated with large language models. However, that's hardly the only applications of those. It's also useful in robotics. So this was a paper that came out recently in Nature, where they wanted to be able to use human feedback for training robotics. This image is illustrative. So here's what's happening is that there is a human and there is a robotic arm. The robotic arm has been trained to avoid collisions. And so that you can imagine as sort of like the reference reward. That's the starting point. And it performs a series of maneuvers. And then you can see that it has the dotted lines represent two trajectories. One is where it avoids that glass and reaches its target red spot, that is denoted by the red, that's closer to the glass. The glass here is a delicate object. The other one is blue. So what they had was, this was a experiment. Actually, they had an EEG machine hooked up to the humans, and they could tell that, if the robot is closer to the delicate object, the humans were more anxious. And so they were using that as a reward signal. So it's kind of similar to the RLHF, where instead of, two trajectories, two text trajectories, you have the robot moving, and it's being given continuous feedback about which one is good. So it's the same thing. And this was an iterative process that was used. And this is you called as inverse reinforcement learning, which means that you're trying to learn the reward, hence the title, Learning to Learn. And then finally, self-driving cars. It's another very popular example of this. Here you can see two different trajectories. One where, the gray car that you have here has narrowly avoided the opposite vehicle, and one where it has not narrowly, it's farther away from it. Obviously, we can hard code the cars to not hit stuff, but these kind of social behaviors that are not as numerical, but they're more in terms of, if someone sees it, they can say which one of those two is better. Those are incorporated into the system using human feedback. Or you can have other types of feedback as well. You can have other sensors that are feeding into it. So the purpose of going through all of these is to just say what is the difference between these two kind of approaches. And now, to make it more concrete, what I will do is I will go through mathematically how these two are different, and that will sort of illuminate our work and why it was important. So for a vanilla RL, in the case where the reward is not being changed by human feedback, a very common way to do that is to take the average reward you get from a policy. A policy is just a rule. If I'm in a particular state, what action am I going to take? And then parameterized by theta. Theta here can be a neural network. If in the robotics case, in the large language model case, this can be a transformer, and the theta is just the parameters that it has. And then you just treat it as a gradient descent problem. So, you get data, you sample data from it, you estimate your J theta, and you do a gradient descent. Now, this gradient descent is calculated using what's known as the policy gradient theorem. There are many variations on it. The PPO, of course, is one variation. But broadly speaking, this is kind of the loop that happens. This is the mathematical structure. Now, in the case of a bi-level RL setup, you have not one, but now two reward functions, loss functions that you have to maximize. And both of them are a function of two variables. So the first one is just your expected reward. That's the same as before, because you ultimately do want a policy that is good, but that reward is now also a parameter of the reward itself. And that reward is a parameter of a function of some function that we have denoted as R phi. And so it's a parameter of phi. Now this phi are the parameters of your reward, typically a neural network in most practical cases. Apart from that, there is also a function that you have to maximize that is a function of the reward itself. This could be, when the human is annotating, this trajectory is better than that trajectory. It uses that function to update the parameters. In the case of, robotics, the robotic arm moving close to the glass is worse than the robotic arm moving far away from the glass. So that's how you used to update those parameters. It's an analog of the expected reward, but for the analog of the cumulative reward, but parameterized for the reward function. Now, that is also a function of the policy, because as I said before, once this loop that you had here, the data you were getting for that human annotation and the driving that is happening is coming from the previous policy. So they are the function of both the class of variables. Now, the reason I wanted to go over it and then write it in this font is that the typical bi-level RL that is done, that is both RLHF as well as the robotics algorithms, typically known as inverse RL that we are talking about, broadly have this structure where you initialize a policy, you initialize a reward model, and then for a certain number of iterations, you keep on looping through gradient descents on the upper and lower loss functions. Typically, this is how it's done. Now, in some cases, the updates on the upper loss function would be one in both of them. So where you only do a single update on the upper loss function and multiple on the lower loss functions, or vice versa. It's kind of up to the specific implementation, but broadly speaking, this is how the implementations are done.
If I may
Yeah.
interrupt and ask a question.
Yeah.
So I have two questions here. The first question is that with the notation you're writing over there, we're updating the gradient of G. Yeah, the
Yeah.
gradient, it's a partial gradient that you
Oh, so-
theta as a
yeah.
constant and only phi or whatever the Greek letter is to be the variable,
Yeah.
or because you're updating, for example, updating gradient of f that's on theta, right?
Right.
And so it's a gradient of theta.
Yeah, so in the first one, it's a gradient of phi, and the second one is a gradient of theta.
So technically, it's not a function of two variables, it's a function of one variable. I mean,
Right, so typically it's treated as such. They say that I'm not going to treat it as a function of the other variable.
okay,
So that's why I didn't use any iteration on it. But the point is that it actually is. And the algorithms that are in use right now are ignoring that. So that is what we are going to.
well, but see, look, if you use the gradient notation and writing two variables,
Right.
technically, the gradient is.
It becomes a partial gradient.
So you technically have a partial gradient with respect to theta here.
Yeah,
right?
yeah.
And but with that, technically,
Yeah.
well, from optimization point of view, this is not really a bad level optimization, it's just automating.
No, that is true. That is true. And I will come to that. So
Okay.
that's the work that we did was to actually modify these to an actual bi-level RL. That is
Okay.
kind of
Okay.
what to go for. And you are correct that the notation here, I'm abusing it a little bit, but it is for that reason. And in fact, this is the next thing that what I was wanting to point out, that what I talked about is that if we're looking at the lower level loss function here, the data that is coming when we optimize this is coming as a function of the reward parameters that have been updated in the previous.
Right, also that's you use the terminology lower level.
Yeah.
With that expression over there, I don't see which one is lower or higher level, because usually, in bi-level optimization, when you have a lower level, you're talking about one of the function being the parameter of the other function.
Yeah. So we will come to that. So the point was that right now I want to show that how it's done
Okay,
and how it ignores the bi-level structure,
okay,
which we account for in the later. Now, that's a good observation.
So when you
Yeah.
say that this is how it's done. So frankly, I have never seen this algorithm as such, okay? Like I know how inverse reinforcement learning works. It doesn't work like this.
So yeah. There are certain algorithms that do inverse
which
learning
one?
in this. So we'll come to an example. It's called Pebble, which sort of proceeds in a similar manner, and that's kind of the baseline that we use to show that incorporating the bi-level structure improves it. Yeah.
Related to machine learning, you say the function is related to the updated value.
Yeah.
But you're not propagating the gradient, right? Just,
No, we don't
So-
propagate the gradient. We just take,
okay,
so the phi improves, and then we just use it phi.
Okay.
So practically speaking, here I learned the reward. The humans annotated it. I updated the parameters of the reward, and then the next loop that I'm running here, I'm running the RL algorithm on that reward that I just
yeah,
got.
so it doesn't loop back to provide gradient information for the reward, it doesn't.
It can, in terms of if it's online RLHF, it does. If it's offline, it doesn't. But in both cases, so the next thing that I was going to say is that in online, it does. That is the case. And that is what is ignored. In like an RLHF, they just keep on going back and forth and there's no relation between them. So that's what the point was, that existing structures all you're doing is you're treating these two loss functions as independent loss function and then saying that the data itself is related, but I'm not going to account for that. I'm just going to ignore that bi-level structure, and then I'm just going to do the independent SGD. Now, as you pointed out, if we want to write an actual bi-level optimization the way it is done in the literature, you have to write it in a form like this, where the upper loss function, so typically this is treated as the loss function that is used to update the reward, that has to be maximized in terms of the parameters, both the reward parameters phi, but the parameters theta that you need, or you need to have in the ideal case, have to be such that they maximize the lower level loss.
So just for me to understand, the lower level problem, the solution is not a single point, but a set.
It is a set. Typically, from a theoretical standpoint, we assume that the lower level loss function satisfies the PL condition.
Okay.
So it can be assumed to have a unique solution, because otherwise the guarantees that we establish are not there. But yeah, to your point, if we treat it as a non-convex, it will be a set and not a unique point.
I mean, even as convex, it can still be a set. It just only if
Yeah.
it's
Strictly
strong convex,
strong.
straight convex.
Yeah,
That it must be a unique.
right.
Okay.
Right.
But in your typical setting, the lower level problem has a unique solution, or it's a set.
That's what we assume. It has a unique solution. We assume that the lower value itself is unique, but yeah, it can be a set. So more formally speaking, this should be like a belongs to and not an equal to.
Okay.
Yeah.
Okay, because I mean,
Sorry.
I just think if it is, oh, well, please continue.
Yeah, maybe, let him continue.
Yeah.
Please continue.
So yeah, just to give a broad overview
Mhm.
of the two things, the RLHF and imitation learning, for which an inverse RL is a part of it. The two upper loss functions are what decide the difference in the problem. The RLHF, what is typically done is two trajectories are generated. That's a common case. Multiple trajectories can be generated, and then you have a function which, based on which of the trajectories are chosen, can update the parameters. Then you can have multiple pairs of trajectories. This is kind of like a logistic loss, it's also called the Bradley-Terry model. In case of imitation learning, like a robotic or a self-driving car, the upper level loss function is given in terms of what's known as the KL divergence. So the data that you get is typically from what's known as an expert policy. So an expert policy would be, some robotic simulation where they have like a predefined idea of what the ideal simulation is. In case of driving, it could be a driver you want to imitate, and then when they follow these policies, the actions, they induce a probability distribution on those two actions. And the aim is to keep those two as close as possible. So your reward that you're getting should ideally be close to the expert.
Well,
So
this is only for inverse RL,
yeah.
not imitation learning in general.
Yeah, it's a specific example that fits in this case. So how can we, the question is that now that we have talked about how they are different, how do we account for this different? Or in other words, what is actually missing from the usual setup that happens? And actually, in order to see what's the additional thing, it's actually not that difficult. So if you just write the gradient of this function g, and if you just differentiate it, it's quite, because this function theta star is a function of phi. Actually, there's a typo here. This should be phi. So the additional term that you get is kind of, you can actually see just from the basic calculus that there is an additional term. Now, the problem is that if you look at this term here, differentiating with respect to phi there's no closed form solution for it, because it's not as if it's related to the maximum value of j phi theta by any function. It's just the optimizer for it. even in the simplest of situations where, it's a banded situation where there is no sequence of action. There is just one action that you have to keep on doing repeatedly. Even in that situation, there's no closed form where you can just say, oh, theta star is, phi square or something like that. So it's kind of hard to explicitly calculate it. But that does not mean that there's no expression for that exists. Is that calculating it is very computationally intensive.
So nobody has used hypernetworks to sort of,
Sorry, what?
so nobody has used hypernetworks to learn that, learn to optimize.
Are you talking about the hyper gradients?
Okay.
Are you referring to hyper?
No, I think I know about the hypergradient paper
Right.
from group in France, but no, a network would essentially learn to solve an optimizer for you, optimization process for you. So it would be a network that approximates the optimization routine if you were to unroll it to give you the optimization. Now,
I guess it could be done for an RL case, but the thing is, then you would have to get a theta and have a problem and get an optimal theta for that, have another problem, get another, and then fit a function to that, right? And so that is just, you have doing multiple RL problems and then.
yeah, we can discuss that.
Yeah, I mean, that would be a thing, but I can, maybe that would be like quite computationally intensive. So the thing is, if we want a closed form of theta star, what we first do is just we say that, okay, because it's a maxima of this j theta phi, that's how it's defined, the gradient of that is 0. And essentially what you do is you just differentiate that with respect to phi on both sides. And so so if you focus, if you focus on this term at the bottom, what you're saying is that at the end, you get a term that has a double derivative of j with respect to theta and phi. The reason that we can't just implement it as it is because if you think about it, a double derivative of a vector is a matrix. Now, if you think about a typical parameter space, it can be in 10 to the power 6 if you're talking about a neural network, like if you're seeing an image. So it just becomes square of that, 10 to the 12. And if you're talking about an RLHF situation, you can have parameters of hundreds of billions. So, you're 10 to the 10s or 10 to the 11s. And so a square of that is just computationally intractable. So this is not feasible. There was a work that we will talk about that approximates this, but the point was that we want to go one step ahead and not have to use this double derivative. So before we go into how we implemented that, I just wanted to go over two environments. So these two environments are known as the door open and walker environments. Now, they're quite self-explanatory in what they're doing, but the point to be noted here is that they are used to sort of train the kinds of algorithm that we were talking about. So in both these cases, when the agent starts off, they have no idea on what the reward is. The system itself has a defined reward functions. They're mathematically quite complicated. So for example, in door open, it's a 7 degree of freedom robotic arm. It has a defined reward function that has been tuned so that in one step, the robot can grab the door handle and open it. And it's done in a way that it's shown here. So which is, sort of more acceptable to us. You can have it in other ways as well, but might not be very desirable for a human. So the agent starts off with not knowing anything. It has to initialize a random reward. But what can happen is that at different time points, it can get expert demonstrations. It can query that from the system. So it's kind of like getting human feedback in both these situations. And so these are used to evaluate the kinds of algorithms that we were talking about. And what happened was in 2024, there was a paper called PARL, a Unified Framework for Policy Alignment in RL, which sort of demonstrated that if we are able to approximate the Hessian terms, we can obtain an improvement in performance. So this gap that they are showing in both these cases, they can close this gap. And the gap is with respect to the oracle, which already knows the optimal way to, walk across and then open the door so they can complete the task in one shot. And the state-of-the-art algorithm that they compared it to was known as Pebble. And this algorithm was essentially a format, one algorithm, the format that we talked about. You take feedback, you update your reward function, and you do the RL optimization at the bottom. The difference here was that they used a version of RL known as soft actor critic, which is helpful or suited to continuous action situations like robotics, where your action of the robot can have like a continuous framework. So as I said, this approach, even though it was able to show that you can get improved performance, uses RL, and because of the special structure of RL, even the Hessian terms were more complicated. There were trajectories of data that you had to observe, and then the Hessians would depend on those trajectories, and there was a lot of calculations that were involved in estimating those. But even then, the exact terms were not available. There were approximations that had to be used. So now the question is, can we use a single, just order gradient terms to do that? And in order to do that, we have to take a bit of a detour. So in traditional optimization, there was a well-known result known as the KKT reformulation, which said that if you have a bi-level optimization, a constrained optimization, I suppose the term they would use, where you can define the lower level as something that is always negative, then the function can be written as a single function, where you have the main function that you want to optimize plus some constant, this is a tunable hyperparameter, times the constraint at the bottom. So this was known as the KKT reformulation. The time when this was much in use, neural networks were not that common. Transformers had just not been invented yet. So even though this was something that could have been used for bi-level RL, and we will come to some examples that did use it, the guarantees that were there that ensured that this will work required that the lower level be a convex function. So
wait.
Yeah.
So this is an optimization problem where you have an optimizer and a constraint, right?
yeah,
But your formulation for the bi-level, you had two optimizations, right?
right. So we'll show that this is not exactly what was used in our case. So this is just like a sort of like a template on which what we used was based upon. This is more of like a simplified situation, which was used in prior cases to go from like a constraint to a single level. But this is not what we used, because as you said, that's not actually applicable to what we were doing. Yeah. So now to your point, what we were looking for is, sorry, you.
I mean, for the constraint H being negative, it's not how you convert to regularization, but okay, I mean, that's not what you're gonna use, so let's
Yeah.
There had to be some more like go back.
Yeah, there are other situations as well, but
H needs to be defined properly, like it should have that J of phi theta minus J phi theta star. It should have that optimality, then only it will.
Right. So yeah. So just like it's a function that so next when we come to it, it sort of has that same structure. So that's what I wanted to connect to it. So the thing was that our problem sort of looks like this. You have a upper level, and then the lower level is sort of an optimality for a lower level loss function. So Kwon et al., they established a formulation where the lower level didn't have to be convex, and then they defined a supplementary loss function, which kind of looks like the upper level loss function plus 1 over a constant. And this is a constant that was a hyperparameter, and then the difference of these two functions. So the difference of these two functions here, so we will come to what this psi star phi is. But if you look at this function here, just from the definition of theta star phi, this thing that 1 over sigma is multiplied by, that will always be negative, because by definition, this thing is a maximizer of this function. So any theta that is here is always going to be less than this. So this thing is negative. So this was kind of, when they were doing this formulation, their starting point was a kind of bilevel formulation like this, where the lower level was supposed to be negative, and then they used sort of an inspiration, because in real KKT formulation, the lower level is written as G, phi theta minus G phi theta star, which is always negative. So they used a similar formulation here. The difference was, or the way they made it to work with a non-convex lower level, is by this defining this other optimal parameter, which instead of optimizing just this theta, just j phi theta, it optimizes a supplementary loss function given by the linear combination of those two loss functions. And the key, one thing to notice is that this is 1 over sigma, and this sigma were the same. And so this, yeah.
I don't see how that is negative unless there are parentheses missing.
Yeah, there's a parenthesis here, that's a typo, yeah. So that's, and so the actual formulation of this was like rather large, where they, and in this one, they just showed like a theoretical formulation that worked. They didn't actually implement it. The theoretical guarantees that they gave were also quite loose. So yeah, so this was the bilevel framework. So, and then implementing them had, there were certain advantages, but there were certain challenges as well. So the advantage obviously here is that this formulation is a single level. There's no Hessian, and there's no inverse of the Hessian as well, which itself is quite computationally intensive. And then, unlike the traditional formulations, the KKT formulations, they don't have to have the lower level as convex. So you can use neural networks and transformers for the lower level. The challenge was that these methods required the formulation of the lower level with respect to the reward parameter. Now, the policy gradient theorem also already has the gradient of these with respect to theta. However, with respect to phi, there was no result that was existing beforehand. So we had to come up with, prove that something is an estimator of that, and then implement that as well. And apart from that, the theoretical analysis also had to be novel, because prior analyses did not account for non-convex lower level and high level setup.
And its function is non-convex.
J? Yeah, the constraint, because it's the linear combination of two non-convex functions. So
The KKT, the nice properties of KKT conditions do not hold.
right, they don't hold, because it's a non-convex function here, so they don't hold. But this paper, Kwon et al., actually showed that this formulation does indeed hold.
But is the G,
G is just the upper loss function.
is that convex
No, that doesn't have to be convex.
for KKT?
No, for KKT, it has to be, not for this. Yeah, there were, apart from KKT, there were other formulations where the upper level could be non-convex, but the lower level still had to be convex. They were also not useful for us because, well, the lower level is also obviously going to be non-convex.
So can you give me the big picture? Because
Yeah.
we started introducing convex optimization, and then the kind of problem you have is one where neither the objective function nor the other constraints are convex.
Right. So
What can you say from the theory of convex optimization into this?
So the reason, what I wanted to say was that the existing theory required either one of or both of them to be convex. For our case, neither could be convex, which did not exist before. And so, yeah, so the algorithmic implementation, it kind of looks like this, but I think what is to be focused on here is that, like in the previous term, previously I talked about how those two optimizations were carrying on independently with each other. The key insight here is that here you see that this gradient with respect to phi, which is the reward loss function with respect to the lower level, this accounts for the effect of the lower level on the upper level loss function, this term here. And then because they defined that other supplementary loss function that was like, J plus J minus sigma G, that the gradient of that term kind of accounts for the other effect of like the upper level loss on the lower level.
So this is yours, this is your algorithm?
Yeah. So it was sort of an implementation of the work in Kwan et al. They had like a theoretical framework where they said, okay, this is going to converge. So, and when we implemented that, what we were able to show that the algorithm Pebble, which is just an implementation of the vanilla bilevel RL that we talked about, if we make these modifications that we just talked about, it was able to improve on the performance on that. Now, I think you can reasonably say that, in the door open, if we had allowed it to go further, it might have, shown even a bigger gap. But the point here was that we wanted to limit the number of queries that you give to the system in terms of the expert policies. So you don't want to, because in real life, the budget for those is limited. So the point was we
put that this way that in real life, 250,000 queries to breaking a glass is plenty.
That is true. Yeah. That is true. So like, I will say that even now, like we are still some ways away to, making an algorithm which can teach a robot in like a practical number of steps, but at least this builds upon what is currently known to be the best. Or
How many samples are used? We get these shaded areas?
I think we used a run of 20 at each point to get the shaded area, the variance. There is quite a bit of variance, but I think we can use, variance reduction techniques and so on. But the point of this was to show that the way that things are being done right now, there is performance left on the table, which can be improved if we account for the bilevel structure. So yeah, so I just wanted to quickly go over the theoretical analysis as well. So the reason why you would want a theoretical analysis is that it tells you how much data is needed to achieve acceptable performance. So if you're applying it in real life, it can give you an idea of how much data is needed. And also, since we are introducing this algorithm to everyone else, if we can give some guarantees about it will work, it will converge at this rate, sort of can encourage them to also use that. So essentially, we did like what's known as the sample complexity. And so we take this quantity here, it just tells you, the norm or the size of the gradient averaged over the number of time steps the algorithm has been run. It essentially is telling you, whether the algorithm has converged or not. So if it's very small, that's an idea that the algorithm has, is not changing much, which is all we can say because the upper level loss function is non-convex. So that's all really we can say. And then, so just wanted to give like a quick background upon what the sample complexity definition is given by. So it's usually given by in terms of big O epsilon to the negative t, where big O is the, the big O notation, and epsilon is a small positive number and d is a positive integer. And essentially what that means is that if you say a sample complexity of epsilon square, that just means that if you set epsilon, 0.01, you require the samples of the order of 10 to the 4 or tens of thousands. So essentially the smaller d, so if it's epsilon -1, then here you just need, 1,000 samples. So it's better than that. So the smaller this d is as a positive integer, the better the algorithm is. And so what we were able to show in that when we, yeah,
the order of 0.01 to the, okay, yeah, that's
right. So what we showed was that this gradient term that we had, it was essentially a component of two different things. One was the inherent randomness of the system, because the system itself was random. So that was one source of the error. Oh, sorry. And then the other one was because we are estimating these two optimal loss functions, we are running gradient descent on two loss functions. There's going to be some imperfect estimation because we don't have infinite number of steps. So the two sources, one of them was the source of an error of the order of epsilon -1. And this was just a function of the number of times the algorithm was run. The other two gave an order of epsilon -2, which essentially was the number of samples we used to calculate these two loss functions. There were other error terms as well. They were negligible compared to these two. So these two errors multiplied because at every point we need to calculate these two optimal loss functions. So it's so we got a total sample complexity of -3. As of now, this is the only sample complexity result for this kind of setup where you have a negative, a non-convex loss function in the lower level. It also improves upon the bi-level literature. So the bi-level literature, even without any MDP structure, the previous result I think was epsilon -6. So it's quite a bit of an improvement on that. Right. Yeah.
So this statement epsilon is about the small, what is epsilon again?
Epsilon is, you can think of it as the gap we want between we can think it as like the quantity of error or the size of the error.
And the minimum argument or the min?
So here we can't really talk about the bin because on the left-hand side, we just have this average size of the gradient.
Oh, okay.
If it was convex, instead of this, there would just have been the gap between our estimate and the optimal. So then it would have been, but now we can say that, okay, we want on average the gradient to be very small, let's say 0.01.
Okay.
So we need that many sample. So this is what we had, and the second error here to the imperfect estimation, we used sort of the analysis we had in the previous year. That was like one of our spotlight papers in ICML. And this one has been submitted to NeurIPS this year. The reviews should, I guess, come out in a couple of weeks. So yeah, just quickly going over other analyses. There were other analyses. One was done by Yang et al., where they recreated the PAL paper, but they did it for an even simpler situation. They were able to get better theoretical analyses, but they could not, improve upon the algorithm in a practical sense. And then Shen et al. Sort of did what we talked about, like a KKT formulation, but because of the constraints of the KKT formulation, they had to simplify their situation a lot. It was sort of like the KKT formulation, not quite, but they could not have a non-convex loss function.
So you started motivation of LLM, right?
Yeah.
So are you going to apply this for LLM?
Yes, that's going to be the next
Okay.
thing. Yeah. So just quickly, just both of these words that we're talking about, they did not show them improving a state-of-the-art algorithm. They just had their own things that, okay, our algorithm is working. So yeah, the conclusion, as I said, this is the first application of bi-level where, we have used a non-convex lower level. We have done a theoretical analysis as well of big O epsilon cube, and we have improved upon current state-of-the-art algorithms such as Pebble. So the future work, as I talked about, we have for now just implemented them in a simulated environment. The hope is now to use other more complicated simulations, such as self-driving car and power grids and other smart grids. For the RLHF, because the prior approaches either were computationally inefficient because they were using Hessians, or they were using very simplified structures, they could not even be applied even in a simulated setting to LLMs. Because if you take away the complicated structure, you don't have a transformer, the LLM doesn't work. So you can't really apply it. So that's the next step. We hope to be able to apply this to large language models. And because RLHF is so ubiquitous, it's used in all large language models. If we can show that, in a generic implementation of RLHF, implementing these will increase performance, that would itself be very relevant. And then, so now to further further extend our analysis into this existing algorithms. Now, this is true for even for RL, but even more so in RLHF. They are very data inefficient. That's been one of the key steps, as you saw even in the simulated. Now, in RLHF, if you have an LLM, the data is computationally difficult, but you can still simulate it if you have access to the weights of an LLM. You can generate data from it. In robotics, that's not the case. If you need real world data, it's very expensive, it's time consuming, and in case anything goes wrong, like you can have other delays as well as financial constraints. So there is an urgent need to make data systems more efficient. One of the examples of this was known as the paper as hybrid inverse RL that was used in ICML, that was published in ICML last year. And what they did was they had a self-driving simulation, and they had a subset of data that was offline, already pre-selected. And what they did was, in the simulator, they would say that, okay, when I'm training my online algorithm, I'm going to supplement it using online data. I'm going to query the simulator, and then I'm going to use that to supplement my data itself. So they were able to show that the improvements they got from that simulation were quite significant, much more so than if they would have gotten offline data of that same amount. So what the kind of the focus of that was that if you have sort of a generative model that you can use while you are training using offline data, that can have very big effects. Now, as of right now, the models that we have currently, not really suitable for the type of data that we have. So quickly, if I go over the types of models, the simplest one is tabular models. So you have a grid, imagine, and then you want to see like, okay, if I'm in a state and take a current action, what's the probability I go to some state, I call it S prime. The simplest way is to do this again and again, count the number of outcomes, and then make a probability distribution out of that. Conceptually, it's very similar. In fact, most of the model-based RL research, theoretically, and the simulation that have happened, sort of use this framework. It only works in finite and small action spaces, and there is no generalization. There is no relation between one box and the other box. Now, if you go a little more complicated, there's known as Gaussian methods, Gaussian mixture models. They are limited to very low dimensional. They do not scale well, and they assume that the data is in this sort of structure, which from a statistics background, this has been useful in a lot of places in biostatistics, but in cases like vision and large language models, it just doesn't work. There's no center limit theorem that you can.
So this Gaussian, mixer Gaussian.
Yeah.
Is used for what? What is you are approximating some distribution?
Yes. So they'll say that if the distribution is multimodal, what they'll say is that I'm going to use a mixture of Gaussian, and each Gaussian will sort of approximate the mode of a distribution if it's very multimodal.
What things does this, so this slide, you say limitation of current models of what?
So a limitation in the sense that they can't really be
Current
applied.
models of what?
Current models to simulate
Are
the.
these applied to all the reinforcement learning, or what is it applying to?
So it's applying to generative models to simulate the system. So
To generative models in general.
yes. Well, the thing was
This
that.
slide is about generative models.
So this slide was how the current models that we have to estimate probabilities or conditional probabilities, how they are insufficient for RL applications. Because I talked about earlier, right?
Okay.
Yeah. So
So they, like what you talk about, there was a lot of functions and bi-level optimization and so on, right? So where was the distribution, mention of distribution there? Where's the distribution?
So we don't mention the distribution explicitly, but as I talked about in the previous slide, that they are doing sort of offline data, and they're using a similar bi-level RL to train the self-driving car. But what they can use is they can use a generative model to supplement their data. And they can use the current information to supplement data that from policies they know are already good to make them better. So it's not as if that mathematically the generative models were mentioned anywhere. It's that when you have a finite amount of data, you can supplement that from a generative model.
So generative model like this distribution will generate data.
More data, yeah. And that generative model is estimated from the offline data that you have. So
Yeah.
it can make it more data efficient. You can, use the data to generate more data.
So you're saying you have some data, from
Yeah.
that you generate your models, then use your models to create and to augment more data.
Yes, yeah, augmentation, I guess, yeah, is the correct term. Yes.
I'm disappointed that you don't talk about uncertainty in your slide, but you have it on your title. I work on
Yeah.
uncertainty quantification. So
Oh,
now I see it, you correct.
yeah.
The second point is we did this work that shows that if you train genetic models on data and create synthetic data and, use that to do some tasks, certain things go bad. So what are your thoughts on that?
So that can be the case, but here what we're doing is we're not just training on the supplemented data. We're just simply saying that we are generating steps using the estimated models. To your point about using the data to train on the data, that is something that I'll just quickly talk about. So diffusion models is kind of the sort of, at least what I think is going to be the cure to this. And what they can do is, if the models are just generating sequences of length 1, then this bias that you talk about, which kind of corrupts the data, can happen a lot. So what they do is, when they use these diffusion models, they generate sequences of like longer length, which are more stable, and they lead to better augmentation. That's something that's been happening, right? So yeah, so as far as Gaussian methods were concerned, they are like very restrictive mathematically. And finally, neural networks. So neural networks can approximate, arbitrary functions, but they are deterministic. They don't learn probability distributions.
Genetic models.
Why not?
Sorry,
Why not?
they can, but they don't capture the uncertainty. So in a neural
What
network,
do you mean? You generate, the output of your neural network is the parameters of a Gaussian mixture model. Gaussian mixture models can model arbitrary distributions.
well, yeah. So
This is
Gaussian
the
mix.
problem.
So Gaussian mixture models, they can, but knowing how many models will fit an unknown distribution, that
10,000.
an NP-hard problem. So that's like something that in statistics, that there's no known method to do that efficiently. So that's why when you're talking about more complicated systems, Gaussian models or like Gaussian mixture models are not, so they don't know like what's the number of mixture that we want to use. Essentially right now, that's like in statistics, that's the issue, that we need a lot of restrictions on the type of data assumptions to be able to say that Gaussian mixture models will work well for it.
So do you need epistemic uncertainty in your RL framework?
Sorry?
So do you need epistemic uncertainty of this generative model in your RL framework that you say generative models don't account for?
Well, yes, because if you want to learn a conditional probability distribution, you should want that the generative model you have would also have a conditional probability.
Oh, yeah, you can also learn conditional generative models.
Yeah,
So
yeah.
I'm trying to understand what variability you're talking about, because you can obviously learn conditional distributions with generative models and so on.
Well, generative models, I'm talking specifically about, neural network functions.
Yeah.
Yeah.
Same, yeah.
Right.
You can learn conditional distributions even over continuous spaces and function spaces.
Well, yes. Oh, okay. I guess since you're talking from an uncertainty quantification, you can learn it. Obviously, you can fit the data and then you can generate the models. What I guess I should have said is there's no guarantee in terms of neural networks.
Yes.
So you can obviously fit it. You can fit a simple
Yeah.
function as well. There's no guarantee that they work. And so that's kind of where diffusion models come in. Because diffusion models have the advantage that, they're trained to generate highly nonlinear, multimodal, irregular data with no restrictive assumptions. Also, they have uncertainty guarantees. Right now the uncertainty guarantees were quite loose in the NeurIPS submission that we had right now. But we showed that we can make the total variation between the unknown distribution and the one you estimate from the diffusion model is the sample complexity is order O to the -6, which is quite big as far as what we just talked about, which is -3. But the something to be noted is that previously this was epsilon negative to the D, where D is the dimension of the data point, which
Yeah,
is
but, I don't see a difference between the fusion models and VAEs. Both of them are minimizing the KL divergence. It's just the way you parameterize the architecture or even normalizing flows. All of them are, so I don't see
Right.
how one is modeling the uncertainty, the other one is not.
well, VAEs can be, but as if I'm not mistaken, both from a performance standpoint, diffusion models do better.
Oh, yeah, performance,
No.
yeah, but,
No.
At least in RL, I've seen.
No, VAEs beat everything in that respect.
So in
That's
case
just
of
not even funny.
So in case of RL, so the literature that we read that there were to generate trajectories, especially in robotics or continuous situations, RL using the diffusion models were outperforming other models.
It's an alternative, but
Yeah.
it's not, no.
Also from like a theoretical standpoint, there were results for diffusion models that said that the total variation between the unknown distribution and the distribution you learn using diffusion models had a guarantee of being epsilon small, depending on the number of samples. As far as I know, I didn't find any for VAEs. They might exist. So
Yeah,
though,
it might have been that people are not working on VAs anymore because.
Probably.
Fusion models, but there was no function space VAs even back then, but now we have them for diffusion models, but that's just because there are people paying attention to.
right. I mean, it might be the case that if we, try to analyze VAEs or other variation we can come up with, but sort of the research and the way it's going, there has been a lot more research in both and plus in, so if you talk about inverse RL or these types of situation, they have to do with image, right? You have to, the state space is an image in most cases.
But inverse RL.
In sort of like, if you think about like the self-driving case, or even the case of the simulation that I was door open. So they have like, the data they are observing is an image. Oh, sorry. So in that case,
Let's take this one offline.
Yeah.
Like we have to kind of wrap up the thing
Right.
and back to voting.
all right. So thank you, everyone. Thank you for coming here.
Okay.
We have another question.
Sure.
You